Right, so this is a diagram of a wave on the sea. Which letter shows the wavelength of the wave? So the wavelength is going to be lots of possible different distances. You might have this is a wavelength, or this is a wavelength, or indeed this is the wavelength. So D is the answer. Which letter shows the amplitude of the wave? Well, the amplitude is the distance from the middle. So the answer is C. A man watches some waves pass his boat. He sees the crest of the wave pass him every 5 seconds. So what they're telling you here is one wave passes every 5 seconds. So the period of the wave is 5 seconds. The frequency is 1 over the period. So that's 1 over 5, which is 0.2. So 0.2 hertz. Okay. Two students, Jenny and Cho, are investigating motion. Jenny walks in a straight line. Cho measures the distance Jenny has walked in a 10-second interval. States 2 measuring instruments the students should use. So pieces of equipment. We're looking for what equipment are they using? So they need the equipment to measure distance, and they need an equipment to measure time. So to measure distance, you could use a ruler. And to measure time, you could use a stopwatch. Okay. You could also, of course, use other things. You could use a tape measure. Or you could use one of those little wheels that you use to push along the ground that goes click, 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 which is called a trundle wheel. But I think the most obvious one is ruler. So now we've got some measurements, and we are asked to draw a graph of the distance against the time for these measurements. Okay. So in 0 seconds, they've walked 0 meters. So I'll put a cross there. In 10 seconds, they've walked 14 meters. So I'd put a cross there. In 20 seconds, they've walked 19 meters. So I'd put a cross there. In 30 seconds, 24 meters. So I'd put a cross there. In 40 seconds, 28. So I would put a cross there. 50 seconds, 30, 60 seconds, 31. Okay, so that is our graph. Okay, so we want to join up these dots as well, and because it's not obviously not a straight line, I would expect a smooth curve, one smooth line through those. So now we're asked, how far has Jenny walked after 35 seconds? So 35 seconds is here. So after 35 seconds, we would say Jenny has walked 26 meters. Describe how Jenny's speed changed during the investigation. So this is a distance time graph, and the speed, if we want the definition of speed, it is the rate of change of distance with time. That's what speed is. So in other words, it's the gradient of the graph. So you can see that Jenny starts off walking really fast, and then as time goes forward, her speed gets slower because the gradient gets smaller. So describe how Jenny's speed changed during the investigation. She starts off fast and then she slows down. Starts off fast and then slows down. Slows down is the important thing. What feature of the graph shows this change? Well, we've already said that the gradient or the slope of the graph, and that slope is decreasing. Oops. The gradient or the slope of the graph is decreasing. Okay, so this question is about electrostatic charges. Complete the sentences using words from the box. Each word may be used once, more than once, or not at all. When a plastic rod is rubbed with a cloth, the plastic rod gains electrons. Okay. After the plastic rod has been rubbed with the cloth, the plastic rod has a negative charge. So we know that electrons are a negatively charged particle. The droplets of paint, so electrostatic charges can be useful during paint spraying. So here we have a spray gun, and then we have lots of spray, lots of droplets of paint. The droplets of paint are given the same charge as they leave the sprayer. So all of these droplets of paint are given a charge. Maybe they're all given a negative charge. Explain why this is an advantage. So we have got lots of negatively charged droplets. And what do you know about negatively charged particles? Well, they repel each other. Okay, so the droplets will repel each other. Why is this an advantage? Well, if they repel each other, then they're all going to spread out. We're all going to spread out and make a nice even covering on the paint. Droplets will repel each other, so the paint is spread evenly on the surface. Spreads out. Spread evenly on the surface. Okay. The droplets of paint are positively charged. Oops, I got it wrong. Okay, so actually all of the droplets are positive, but the same thing applies. Okay, the droplets will repel each other because they're all the same charge. So like charges repel. Okay. The object being painted, so the droplets of paint are positively charged. The object being painted is given a negative charge. Explain why this is an advantage. So again, we have got our spray gun making lots of positively charged particles all coming out. And the object that they are trying to spray, the object has been negatively charged. So why is this an advantage? Well, it means that the paint is going to be attracted to the object. Paint is attracted to the object. And it's even around the back. So even around the back, the spray, the paint will go all the way around the back and stick to the object. Paint is attracted to the object, so the paint will stick to the back of the object, and that means that the paint doesn't just go off to one side. Less paint is wasted. Okay. So give one hazard caused by electrostatic charges and state how the risk from this hazard can be reduced. So one of the examples you might have looked at might have been when you were filling up with petrol or something. So you might have like a big, like an aeroplane, a big aeroplane, and when they fill up an aeroplane with fuel, when they fill it up with fuel, what they do is they have the fuel line, but then they also connect together the plane with the petrol pump, the fuel pump. They connect it with a wire. So this is where the fuel goes, and then this is where the wire goes. So how do they, why do they do that when they're filling up their plane with petrol? Well, the reason is that the fuel can be charged. The fuel might have a charge. Now, you probably experienced this a little bit when you're in a car. Sometimes when you get out of the car, you touch the car and you get a shock from the car. It's the same with an aeroplane. It can build up charge. So you might get a shock. But if you do this to it, it's called earthing. Then you stop the risk of that shock. So the hazard is that there might be a spark or a shock. This, if it's lots of fuel, this could cause a fire or something. Okay, it could fire or explosion. So that's the hazard, and then we got to say how the risk is reduced. So what do? The objects are connected to Earth, okay, to stop charge building up. Okay, good. Right, so this picture shows a runner. As he runs, the runner gets hot. To avoid overheating, his body sweats. As the sweat evaporates, it cools his body. Use ideas about particles to explain why evaporation leads to cooling. Okay, so what we have is we have a hot person, and this hot person is sweating, and then the sweat particles are evaporating off his body. So what do we know about heat? So as he gets hot, the particles of his body vibrate more. Okay, the particles are vibrating much more as he gets hot. So what we have is the surface of his body with lots of particles which are all vibrating a lot. Now, if we've got some water on here, his sweat on the surface of his body, then also the water particles are going to vibrate more. When they vibrate more, they evaporate. So you have the fast moving particles leave. They evaporate. The fast moving particles leave the body. The fast moving sweat particles, because it's hot, the sweat is hot, fast moving particles, sweat particles leave the body. Now what that means is that in total, the average speed of the particles in the body has decreased. And that means so you get to the particles vibrate more, the fast moving particles leave the body. So the average speed of the particles in the body has decreased. So the temperature has decreased. Okay, so at the end of the race, the runners are given a shiny foil sheet to wear. This stops them cooling down too quickly. Suggest why a runner might cool down quickly if he does not wear a foil sheet. So if he does not wear a foil sheet, then the sweat will still be evaporating, but he himself is not making more heat. So the sweat still evaporates. So he is still cooling down, but he is not making any more heat. So he's going to get cold. So how does the foil sheet reduce the heat loss? Well, we know a little bit about heat loss. We know that there are 3 ways. What are the 3 ways? There's conduction, there's convection, and there's radiation. So we know that the foil is a bad radiator. It's bad at radiation. That's one thing we can say. The foil is a bad radiator. So it does not lose any heat by radiation. So the body does not lose heat by radiation. Now the other thing it does is if this is the person again, if you put a surface over that person, the foil sheet, then in the gap here, the sweat, it cannot evaporate, or it stops the convection around the body. So the foil, just like any clothes really, provides a layer to stop heat loss by convection. Okay, that's the second mark. Okay, so this student investigates the principle of moments. He connects a ruler to a stand with a pivot. He hangs a 2 Newton weight from the 60 centimetre mark, and he uses a force meter to hold the ruler horizontal. The scale on the force meter reads from 0 to 10 newtons. How could the student check the ruler is horizontal? 2 ways you could do it. You could measure this height and measure this height and check that they are the same. Or you can use a spirit level, which is one of those little devices which has a bubble, a little bubble in it, which you can use. If you turn it, the bubble moves. So you can use measure the height above the bench at each end of the ruler and check they are the same. That's one method. Or you can use a spirit level. The bubble should be in the centre. State the equation State the equation linking moment, force, and distance from the pivot. Well, okay, so moment is equal to the force times the perpendicular distance from force to pivot. So it has to be a perpendicular distance. Here is the distance. The force is this way. So the distance is perpendicular to the force there. Calculate the moment of the 2 Newton weight. So this is 2 newtons, and they tell you that it's 60 centimeters. So this here is 60 centimeters. Okay, so force is 2, and the perpendicular distance is 60. Now that's going to be 120. Newton is the unit of this, and this is centimeters, so Newton centimeters. That's okay. Or you could do 2 times 0.6 meters to give you 1.2 Newton meters. Either of those is okay. So the student holds the ruler horizontal with the force meter at the 10 centimeter mark. He expects the reading on the force meter to be 12 newtons. The actual reading is 10 newtons. Explain why the correct reading should be larger than 12 newtons. Okay, so let's have a look again what's going on. So why he expects it to be 12, but it's actually 10. So why is there a difference? Well, the one thing we haven't included is the weight of the ruler itself. The ruler also has a weight that we have not included. That's the problem, isn't it? Explain why the reading should be larger than 12 newtons. The ruler has weight, which acts at the centre of mass of the ruler, and that will also cause the ruler to turn clockwise. The ruler to turn clockwise. Okay, so now it says, explain why the actual reading is only 10 newtons. So why might this give you the wrong reading? Well, the one thing we have to look at is that the scale on the force meter reads from 0 to 10 newtons. So it cannot read more than 10 newtons. So the student has chosen the wrong type of Newton meter. So that's quite a trick question, really. The actual reading is only 10 newtons because the maximum reading on the force meter is only 10 newtons. So a picture in the student textbook shows 2 fishermen using a pole to carry some fish. Fisherman A and fisherman B feel different forces on their shoulders. Use the ideas about moments to explain why fisherman A feels a larger force. Okay, so we've got to put the forces on this. There's going to be the weight of the fish, and then there's going to be the force on this shoulder and the force on this shoulder. And they're saying that this force A is bigger than this force B. So why? Well, a way to look at this is to actually look at the distances that are on here. We'll call that one the distance XA, and we'll call this the distance XB. Now, from the centre, that force B, and that causes the thing to turn that way. This force A causes the thing to turn this way. But that distance is bigger. So if this distance is bigger, then the force can be smaller. So this force is smaller than this force. So use ideas about moments to explain why fisherman A feels a larger force. If you consider moments about the fish, and like we said before, if clockwise must equal anti-clockwise, clockwise moment, clockwise, the one that turns it clockwise of FA must equal the anti-clockwise moment of FB. Distance to FB is smaller than the distance to FA. So FB, distance to FB is bigger than distance to FA. So FB must be smaller than FA. Okay, I think that's the best way to do it. You consider the moments about this point. This force will turn it that way. This force will turn it that way about the fish. Okay. Okay, so a question about power stations. Which part of the power station is heat usefully converted to kinetic energy? So where does the heat get changed into kinetic energy? Well, we've got steam coming along here, and then that steam is used to make this rotate inside the turbine. Which part of the power station is kinetic energy useful to convert to electrical energy? Well, the generator takes that motion and changes it into electrical current in the generator. Okay, see the generator. Right, a transformer is used to convert 25 output from the power station to 115 kilovolts. State the equation linking power, voltage and current. Well, that's a nice simple one. P is equal to I times V. Power is equal to current times voltage. Compare the input current and the output current of the transformer. Assume there are no energy losses in the transformer. 3 marks. So for a transformer, we know that we have, if there's no energy losses, power in must equal the power out. Okay, that is if we've got no energy loss. So we should have the current in times the voltage in must equal the current out times the voltage out. So the voltage has been made a lot bigger in the power station. And if the voltage is made a lot bigger, then the current must be made smaller. Okay, if this is big than that, then this one must be made small and that one must be big. So a large output voltage must mean a smaller output current. What is the advantage of transmitting electricity at high voltage? Well, a higher voltage means lower current, and a lower current means less energy loss in the wires. Okay. So some power stations use uranium as a fuel. Now, we looked at lots of different types of power stations. And uranium was one of them in the nuclear power. And we looked at the advantages and the disadvantages of all the different types of power station. Okay, and you filled in a big table explaining all of that. We used the computers to do some research, on the laptops as well. Describe the problems that arise from the disposal of waste from this power station. So nuclear power, what are the problems with it? Okay, so uranium is radioactive. Okay, that's one problem. It emits radiation. We haven't really studied a lot of detail about radiation yet, but we know that it is radioactive. And the other thing about it is it has a very long, what's called a half-life. Half-life. It will be radioactive for thousands of years. Okay, so that's another problem for it. The other thing about it is that uranium is a dangerous thing. Uranium is also used in nuclear weapons. So a part of a problem for it is that it is tempting to terrorists. It seems like a silly thing to put in a physics paper, but it must be stored securely. Must be stored securely. You've got to make sure that people can't come and steal it or something. That's 3 marks. Another thing about it is a human aspect. You don't want to have nuclear waste near where you live. So nobody wants to have a nuclear power station next door to their house. So another problem is that there are few appropriate locations for the storage of nuclear waste. So that makes it very expensive. All of these things make it very expensive. So there's lots of problems with nuclear power. Okay, so the last question is all about gases. And this experiment. A student blows up 2 balloons to the same size. She puts one balloon into a freezer. After a while, the student compares the 2 balloons. The balloon that has been cooled is smaller. Use ideas about particles to explain why the cooled balloon is smaller. So we know that as the temperature decreases, the particles move slower. Okay, they have a smaller kinetic energy. Now, what that means, that if they're moving slower, the particles will collide. Particles collide with the surface less frequently. There are less collisions. Okay. Particles collide with the surface less frequently, on average. Now what that means, and also because they're going slower, particles collide with the surface with less, because they're going slower, they're colliding with less force. Now, because they're less frequently, less often, and they're less force, this means the pressure is less. And if the pressure is less, then it means the balloon is going to shrink. The pressure inside gets smaller. The pressure outside pushes it in. So this is the pressure is less inside the balloon. Pressure outside pushes the balloon inwards. So the volume decreases. Okay, good. So the student is now trying to do an investigation between the link. The student decides to investigate the link between temperature and the size of the balloon. She writes a plan. You'll change the temperature of the balloon by putting it into a freezer. To get a range of temperatures, I will put the balloon into the freezer for different times. I will measure the temperature of the balloon using a thermometer. To measure the size of the balloon, I will take it out of the freezer and line it up next to a ruler. To make sure it's a fair test, I will repeat the experiment 3 times. I will plot a graph of size against temperature. There are several faults in the student's plan. Identify 3 of these faults and suggest an improvement to correct each one. Now, we know that the important thing about gases is not the size of the balloon at all, but the volume of the balloon. So I think that is the first fault that I notice. Okay, the size of the balloon is not precise. What we need must measure the volume of the balloon. So that's one thing, measuring the size of the balloon. That doesn't mean anything to measure the size of a balloon. You've got to measure the volume of a balloon. Okay, the next thing I notice is that she's trying to use a thermometer. Now, how could you can't just put a thermometer next to the balloon and it will give you the temperature. A thermometer will be difficult to use to measure the temperature. So it doesn't give you the temperature of the gas. It won't give you the temperature of the gas in the balloon. So how will you make that better? Well, I think you need maybe to use the temperature of the freezer, actually have different freezers with different temperatures, or even maybe do it with hot temperatures and put the balloon into a bath of water and measure the temperature of the water or something. Okay, that might be a better way to do it. Place the balloon in. Oh, in fact, we did a very similar experiment, didn't we? we had this thing with the gauge on it, and we put that under the water, didn't we? We looked at how the temperature changed the pressure with the pressure law. Place the balloon in a bath of water at a known temperature. Okay. And the third difficulty is, I think, that this isn't going to work very well either, is it? To get a range of different temperatures, I will put the balloon into a freezer for different times. The balloon will change temperature really quickly. It doesn't. This won't give you lots of different temperatures. So the third fault is that the balloon for different times in the freezer will not give a range of temperatures. And again, the best method, I think, is to use maybe lots of different water baths. Use different water baths with different temperature, or many freezers. At different temperatures. Okay, and that's the end of the paper. Well done.